Thank you, Mark. And thank you to the Faculty Senate for selecting me for this award. As my title indicates, I want to talk to you today about how minds have changed over time. And I want to tell you that story from my perspective as a woman professor in chemical engineering who has a research interest in bioengineering and life sciences. So in thinking about the time back to 1981 when I was first an assistant professor at Mines, I was actually struck by how many similarities there were to today. In 1981, oil prices were high. Minerals prices were high also, and they're going up now. Resource supply concerns existed. We were worried about running out of things. Oil shale was being developed on the western slope, and because oil prices are high, they're thinking about it again. And even Jerry Brown. Even Jerry Brown, his signature is on my PhD diploma because I graduated from the University of California, is governor again, although at least his hair is grayed, and so there's been a few changes. He doesn't have as much. At Mines, there was a number of similarities as well. The student body had just doubled, and the number of faculty was growing in response. We'd graduated about 100 women. Not too different from today, in fact. We've graduated a few more women, and now we have some masters and PhDs, but otherwise remarkably similar. But of course, as all you know, there's a bunch of differences as well. In 1981, we declared and boasted that we were the world's foremost school of minerals engineering. About 80% of the degrees we granted were in the earth science and resource disciplines, and even our economics program had the name minerals in it. Today, we describe ourselves more broadly. Colorado School of Mines, Engineering the Way, or Colorado School of Mines, Earth, Energy, and Environment. And those of you who aren't part of the Mines family here, you at least see these in the airport. Fewer than 40% of our degrees are now in the earth science and resource disciplines, and our economics program has lost minerals from its name. In 2011, we now have 32 women professors, which is an increase of a little more than 5-fold from the 6 we had at the start of 1981. But it's not these differences that I want to think about today. What I want to focus on today is the evolutionary process in response to change, especially the successful response to change. Moreover, I want to propose that there are 3 actions that are commonly present in the successful response to change. The first of these is make a plan. So this is where you sit down and look at what the changes are that are happening around you, and you decide what you need to do or what you want to do in response. The second action, I think, is seek diversity. For organisms adapting to changes in the environment, it's genetic diversity that matters. If the gene pool is too small, the species doesn't survive. And so successful species have developed behaviors that promote genetic diversity. I think that individuals and institutions have to be seeking the diversity to successfully respond to change. In this case, the diversity is in knowledge, talent, skills, interests, points of view. An academic institution seeks diversity by hiring more diverse faculty. As individuals, we seek diversity by surrounding ourselves with individuals that aren't just like us. So we're more successful when we work with teams with lots of different interests or different points of view. The third one is enjoy serendipity. Now, you of course remember that serendipity means achieving a desirable result by accident. So this one's sort of a passive one. You do this step sort of after it happens. Often these are accidents of timing. You know, the chance meeting, the chance conversation, then it leads to a long-term and productive collaboration. So with these 3 actions in mind, I want to explore this theme of responding to change with 3 stories of how Mines and its faculty have evolved in response to changing times. But let me first tell you a little bit about the changing times we were working in. I want to start in 1970. Guy McBride had just become president. It's interesting that I included this because he just passed away. He had started to implement a plan to double student enrollments. Women's rights were important, and the environment was important. And so in 1972, we saw Congress pass the Equal Rights Amendment. And the first Earth Day celebration happened that year as well. At Mines, we reached a milestone of, for the first time, having 100 women students on campus of a total enrollment of about 2,000. In 1974, we hired our first woman professor. Later in that decade, the Environmental Sciences and Engineering Ecology, we called it then, department was started. And a year later, our board of trustees decided that every student who graduated from Mines had to take a course in environmental science. Overall, in the 70s, 153 women graduated with degrees from Mines. A truly remarkable achievement if you realize that in the more than 100-year history before that, only 14 women had graduated. Overall, the 70s were a time of tremendous growth, fueled actually in large part by huge increases in oil prices, which peaked in 1981 and then began to drop even faster than they had risen, was disastrous, or at least caused big changes at Mines. So the 80s, before the prices began to drop to 1979, when prices were still high, Exxon began the Colony Oil Shale project out in Rifle, Colorado. It was estimated that the cost of this project would be at least $5 billion. 2 years later, I joined Mines as an assistant professor, and my husband, we had the classic two-body problem. He had to find a job. To be honest, that's the only reason I ended up at Mines. I had a couple other places I wanted to go, but he never found a job. Well, he took a job. The irony of this is he took a job with Exxon's partner on the Colony project. Unfortunately, our move to Colorado pretty much coincided with the start of the drop of oil prices. And as oil prices started to fall, Exxon concluded that they couldn't possibly make Colony profitable. And so after spending more than $1 billion, they canceled the project. And May 2nd, 1982, which became known as Black Sunday, it's memorable for me. It was the same day I ran my first marathon. I came home all excited, and then we discovered Colony had been canceled. It was the first sign, or one of the first signs, that the oil boom had gone bust. And it was going bust in a really big way. And for me personally, it was a problem, because my husband worked on the Colony project and lost his job. Employment declines weren't just for my personal case. Our former graduates were losing their jobs, and our new graduates were having a hard time finding jobs. And because of the bleak employment situation, student enrollments dropped. Always a problem for an academic institution. Over the next several years, oil prices continued to drop, reaching a low in 1986, where they stayed pretty much around for more than a decade. To make things even worse, mineral prices collapsed too. And it was about this time that George Ansell became president of Mines. And he described this time as a period of abrupt, discontinuous change. He went on to say that the world of energy and minerals, right, the world that Mines had lived in for over 100 years, was no longer narrowly focused nor slowly changing. And you either had to change the world or change the school. And changing the world's a really hard job to do. So the school had to change. It was a sign of the times that we saw this bumper sticker around. Please God, just give me one more oil boom. I promise not to blow it next time. We should keep this around. I have a feeling we might be needing it again. So I'm going to tell you 3 stories, starting with the first one. You've come a long way, baby. This is the story of women joining the faculty at Mines. Now, I've been here for most of this history, but even I wasn't sure about the details. I tried to remember how many women had Mines hired, what had happened to them, and could we learn from their history. And since I didn't remember the details very well, I set about looking for the data to find the answers. Now, I thought this would just involve a few phone calls to find the right person somewhere who had this information on their computer or in their filing cabinets. Well, I never found that right person. And if they're here, I would love to know about it. So I had to assemble the data myself. Most of the data I've collected is from the, you may have forgotten this, I had. There's a faculty directory at the back of every student bulletin, which is issued each year to tell students what they have to do to get their degrees. I supplemented it with some information from Human Resources, which was just a little the student yearbooks. And with respect to the women, direct contact when I could. So on women, what I tried to find was when they started, when they were promoted, and if they're no longer here, when they left. For the men, the only information I have are numbers. The number of male faculty over the years. So I have a little bit different information for the two groups. I included anyone who had the rank assistant professor, associate professor, professor. I didn't include those who had lecturers, who were titles of lecturers, instructors, or they were professors with other qualifiers other than just assistant and associate. And this was just a practical decision because the information for these groups was incomplete or just completely lacking. Okay, it will be helpful for you as I present some of the results of that data if you understand this academic structure. And I know there's some people here who might not be familiar with it, so let me just review it. The life cycle of a professor most frequently starts by being hired at the assistant professor rank. Not always, but most frequently. And then subsequently promoted to associate, and if you're really good, you make it to full professor. And just to make it clear, we refer to a professor as full. I'm not quite sure why. It sort of implies that associate and assistants are only partials. True. It's true. Of course, faculty can leave from any of these ranks. Assistant professors, though, are restricted to 7 years. They either have to get promoted or they leave in 7 years, and there's no time restriction for the associate and professor ranks. Now, you can be hired directly into associate or professor, but it occurs less frequently. And the statistics on the women in mind, I know exactly. Only 14% of the women have been hired directly as either associate professor or professor. So in considering this academic structure, we can see ways to increase the number of female faculty. We either hire more or we keep more, retain them. And we'll keep those two ideas in mind and come back to them after we look at some of the numbers. So let me start by just reviewing how many faculty we've had in Mines since 1974 as a function of academic year. Remember, 1974 is when the first woman professor was hired. So during those early years, student enrollment was increasing, doubling, and so the faculty numbers were increasing as well. And we reached a maximum of 185 in 1984. That was a little more than a 50% increase from the low of 120. As enrollments dropped, faculty numbers dropped as well, and we reached the next low of 156. And then there was just sort of a level period and a slow increase until today, where again we have increasing student enrollments and the faculty numbers are increasing as well. You might find it interesting, those of you who are faculty, that we haven't exceeded this 185 number until just 2 years ago. And we're now we're very close to 200. The number of women on the faculty during this time increased from 1 in 1974 to 32 today. Now let's look at the women faculty as a function of their rank. And I'm going to list them by department using the current department name because some of the departments have changed names. And they're in alphabetical order. Chemical engineering, chemistry, economics, engineering, environmental science, geology, geophysics, liberal arts, math. You're remembering all these, right? Metallurgy, mining, petroleum physics. The first woman was Julia Alexander, and she was hired as an assistant professor in humanities in 1974. A year later, the second woman came. It must have been really hard being the second person in mathematics. Third one was Joan Brooks in engineering. They were just putting one in each department at the time. And then Amy joined in geology. 1977 was a special year because Betty Willard was hired as the first full professor at Mines, hired in directly. Not only that, she was the first female department head, and she was the first department head of the environmental science and engineering ecology was then the name of the department then. In 1978, Ruth joined in mineral economics. Joanne Hackos replaced Julia, who had left in humanities. 1980, nothing happened. But in 1981, you could say all hell broke loose. Mines hired 8 assistant professors. And now what's remarkable about this is the pool at that time was really small. But Mines used this time when it was increasing the faculty really rapidly to really aggressively go after women. And I was in that group. So just before I came, there were 6, and then suddenly there were 14. We now occupied 8 departments out of 13, for those of you who don't know the total. And the first woman was promoted to associate professor. Because student enrollments declined after that, the numbers stayed relatively flat, and there was some shuffling between the ranks as people were promoted, and some people were hired and some people left. And if we fast forward to 1987, now you can see, because we haven't hired many new assistant professors, everyone's an associate, all the women are associates. And if we fast forward, the next significant year is 1991. There's now women in 9 departments, 18, we're averaging 2 per department. But what's significant about 1991 is we now have 3 full professors. 2 of them hired at that rank, including Joan Gosink, who became the 2nd female to be a department head. And this is when I became the first female to be promoted to full professor instead of being hired directly. If we fast forward, the next significant year is 1997. We now have women in 10 departments. And we can keep fast forwarding, slowly increasing until this year, 2010, 2011. We now have 32 women in 10 departments. What is kind of interesting is there's 7 full professors now. And all but one of them is in duty as a department head, associate provost, or head of a campus-wide institute. And the one who isn't in administrative duty, holding administrative duties, just retired in January. So they're counted in this year, but they've only been here for half the year. Overall, since 1974, the total number of women have been hired are 68. There's been at least 1 woman in every department except for mining. And there's sort of the expected trends. The departments that have had more women were in disciplines that had more female PhDs available to hire. And the smaller numbers were in disciplines with fewer female PhDs. By the way, that's really tricky to say. Fewer female PhD. Also, in some departments, there have been small numbers of faculty, and they've been relatively stable. So there just haven't been any positions filled in a number of years, and that's one of the problems with mining. These are the total numbers of women since 1974. We know, of course, that the number of faculty was changing too. So it's more interesting to look at the percent that women are in terms of the faculty, and I show that here. So you see that big jump, a doubling in the percentage from 1980 to 1981, and then a slow increase until we reach 13% in 1994. And then it stays relatively stable except for a little drop here. This year we finally reached 16%. This is really interesting, I thought. I hadn't realized this. The number of women in the last 16 years, since 1994, had increased from 21 to 32. But on a percentage basis, it was only 3%. If we analyze the data looking just at women faculty in the departments that are represented by that are science, engineering, math departments, it doesn't look any better. In 1994, 10% of the women, 10% of the faculty were women. And 16 years later, it was only 2% more. And what's interesting is to compare these numbers to a report released just this week from MIT for the same period of time, pretty much. When they looked at their science faculty, they found that it increased from 8% to 19% in women, and engineering had gone from 7% to 16%. So in 1994, Mines was ahead of MIT. But we stalled. And MIT has increased. What happened? Well, let's go back to those 2 ways we can increase female faculty numbers. Did we hire more? Well, let's look. And what I'm going to look at is just the last 7 years. In the last 7 years, I know that we've hired 15 women as assistant professors. And we're going to focus on the assistant professor because that's where most faculty start their careers. Now, I don't have information at that same detail for men. So I don't know how many we've hired. But I know that right now, today, on this campus, we have 40 male assistant professors. That means, because of the 7-year time limit, that over the past 7 years, we had to hire at least 40. So we know that we had to have at least 40 men. So we have to have had at least 55 assistant professors hired. So what we can conclude then is of all the professors we've hired at the assistant level, only 1 in 4 has been a woman, 25%. So at least it's a bigger number than the 16%, but we're not going to make progress very fast. Well, so to the question, have we hired more? Well, relative to men, not really. Frankly, this surprised me. I knew we'd hired a reasonable number of women. What I didn't realize is we'd hired so many men. All right, what about retention? How have we done here? Well, I'm going to look again at the assistant professors. So there in 2004, 7 years ago, there were 10 female assistant professors. In the last 7 years, 4 of them were promoted and 6 left. We retained only 40%. Now, I don't know what the numbers are for men because I don't have information at this level of detail for them. But I can say hiring and getting a new professor started is a really expensive process. And whether it's men or women, losing them is an expensive and costly loss to the institution. So I think we really should probably be looking at that retention number for both men and women. So if I were going to summarize women professors at Mines, I would say, first of all, everyone seems to be in agreement. A diverse faculty strengthens Mines. And Mines, I do believe, is committed to creating diversity by hiring more women. The problem is the way we're doing it just isn't working. In the past 16 years, we've increased the number of women on the campus by only 3%. And the data from MIT says it doesn't have to be that way. We can do better. Now, one of the problems, of course, is the pool of qualified women who also happen to be willing to take a job as a professor is just small. And then when you combine that with the recognition that, you know, every time we hire a professor, it really is an accident. It's an accident of getting the timing for when we're searching to match up with the timing for when the candidate is available. And it doesn't take an advanced degree in math to realize that that accident isn't going to happen very often if your pool of qualified individuals, which it is the case for women, is very small. So I think this is where, remember that other action plan? This is where we need to plan. I think we have to start thinking about ways to make that accident happen more often. Now, we can't usually change, in fact, I don't think we can change at all, the timing on the candidate, right? They're ready to go take a job when they're ready to take a job. But maybe we can change the timing on Mines searching some way to introduce more flexibility so that accident can happen more easily. Another idea is to adopt strategies used by our industrial friends. You know, they don't wait until the candidate is just about to graduate and ready to be employed. If there's a diversity candidate that's really qualified that they want, they start recruiting them 1, 2, 3 years before they're going to graduate. Maybe we could do that. Another strategy that doesn't change the frequency of the accident but maybe makes it tip in our favor is to change the climate at Mines to make it more attractive for the for the competition. Now, let's face it, we do have to be competitive with startup packages. But we don't necessarily always have to be the best, right? I bet if we checked around this room, there's a bunch of faculty who took a job at Mines, even though Mines didn't give you the best offer. You took it for other reasons. And so we got to make those other reasons maybe better so that we look more attractive than our competition. I think for women in particular, work-life issues are really important. And I think if you go back and look at the MIT data and what they've done, this is what they changed. They changed the climate in the work-life area. So that's the end of the story on You've Come a Long Way, Baby. After looking at the data, I've decided we didn't come as far as I thought we had. And I'm actually become convinced that we're not going to change the percentage on women at Mines until we change how we recruit them. Chapter 2. Wrapped up in my research. This is my story. And how my research changed in response to changing times. All right, remember I joined the faculty in 1981. My research area when I was a PhD student was enhanced oil recovery. So this is techniques you're using to get more oil out of the ground than you do using standard techniques. Unfortunately, it's a little more expensive, so when oil prices dropped, people couldn't do it anymore. And the research funds went away. And oops, I had to look for another research area. So the next research area I decided to choose was underground leaching of minerals. It was sort of similar to enhanced oil recovery. It involved pumping fluids up and down underneath the surface of the earth. And I did get one NSF project funded in this area right before minerals prices dropped. And, well, you know the answer, strike two. That one wasn't going to work anymore either. So the next one I took up was wastewater cleanup techniques. And I got funded by the Environmental Protection Agency. And you might remember that Ronnie became president in 1980. And by 1984, EPA's budget had dropped by almost 50%. Yeah. OK, now I was lucky we weren't playing baseball. So I wasn't out. But I did decide, I made a plan. I needed a research topic that would be funded by more than one agency. The trouble was I couldn't figure out what that topic was going to be. OK, now I got really lucky. Here's Serendipity raising its head. I met the human rat skin flap model. All right, I bet you're wondering what that is. When engineers talk about models, they mean equations. When biologists talk about it, they mean animals. So this is a rat. You might be able to understand what it is better if you look over here. So basically, it's just a rat that has a flap of skin that happens to be human. And the group at the University of Utah was measuring how chemicals went through human skin using this model. And what they would do is they were measuring absorption of a chemical over time. And what they expected to see was an increase, and then it would reach a plateau where it would remain constant. And what they were seeing instead was the absorption rate would go up after that was applied to the skin, and then it declined. And they had the hypothesis that the skin was sensing that chemical absorption was occurring, and it was adapting and trying to change to slow it down. And that was kind of an interesting question to know the answer to, because it had a big effect on your patch delivery of a drug, if your skin would recognize that it didn't want to let things through. Now, I thought this was an interesting question, and I talked to them for a while, and we concluded I had some expertise that would be valuable to the project. So we organized a sabbatical for me to work at the University of Utah on this project. Now, I was really excited about the project. But if I'm honest with you, don't tell my department head I didn't tell him this part when I wrote my request for a sabbatical. What I was really excited about was being in Utah in the wintertime. And the skiing was really good. But that's another story. So I think you'll understand the results I'm going to show you for the rat model a little better if you understand how it's made. You start with a nude rat, and that means he has no hair, not that he has no clothes. And you turn the rat over, so now it's abdomen up, and you make a U-shaped incision on his abdomen. And then you pull that layer of skin back, and on the part that you just pulled back, you graft a layer of human skin. And on the part where you pulled it back from, you put a layer of rat skin. And then you let it heal, and you have a human skin. Human rat, I never can say that, human rat skin flap. The only problem is if you leave it on the belly of the animal, they can chew it off. So what you do instead is you make a little slit, and then under the skin, you pull the flap around, and you pull it onto its back, and so it looks like this. So basically, what you have is you have something other than a human that has human skin, so you can do experiments on human skin without doing them on humans. Did you get that? OK, so when you conduct the experiment, what you do is you put the rat to sleep so he doesn't wiggle. And you pull the flap out to the side. And here I'm showing the view in cross section. So I have the human side of the flap on the top and the rat side on the bottom. And I take a ring and I glue it on, and I fill it up with the solution that contains the chemical I'm interested in measuring absorption for. There'll be blood flow through the flap, and I'll measure that using a laser Doppler velocimeter. And then I don't do any of this, of course. The people who were doing the experiments did. Then they create little incisions and take blood samples that they measure the concentration to and from the flap. And using that and the blood flow rate, you can calculate the absorption rate. Here's what the experiment looks like. Here's the rat, this human side of the flap, the chamber holding the solution. The velocimeter is here, shown over there. And here's the blood sampling. And I apologize if you're squeamish about blood. Here's what the experimental results look like for one experiment. This happened to be for benzoic acid. So this is the absorption rate as a function of time. And as I already showed you, what they were seeing was an increase. That was expected. But then we were expecting it to remain constant, and instead it was dropping. And the hypothesis we were testing was, did the skin recognize that something was going on and improve the barrier? Now, as an engineer, the first thing I did was calculate roughly how much chemical I thought was going through the skin. And when I looked at the volume of the solution, I thought that the concentration was probably decreasing as it was being absorbed. And so I asked that question, did the concentration decrease? And so we went back and we measured it, and sure enough, the concentration decreased over time. And so this could potentially explain the results. But what we wanted to ask next then, was that rate of change sufficient to explain the rate of change in the absorption rate? And so to answer that question, we did some simple mathematical modeling. I included this just for the few people in the room who might think calculus was meant to torture students. Now, although these equations look a little complicated, they have a very simple physical meaning. The first equation just describes how chemicals absorb through the skin. The second one describes how the chemical goes from the solution to the skin. And those boundary conditions just say what the concentration starts at and that it can't go below 0. So what happened? Well, these equations include some parameters that we don't know. So what we did was we forced the model to fit this curve and then required the maximum to occur at the right time. And then we could calculate the model results here. And so based upon this change in concentration, the model said there'd be this decrease. Now, it's not exactly a match. The trend's right, but the experimental data differ from it a little bit. What I haven't told you is the blood flow rate actually isn't known very well. The measurement technique in this case isn't giving you really good numbers. So probably the answer to this question, does this amount of decrease cause this decrease in rate? The answer is yes. We wanted the concentration in that chamber to stay constant. So we redesigned the cell so that it could be attached to a much larger volume of solution. And you couldn't put that all on top of the wrap flap, so we put it at the side and then circulated. And at the same time, we set up a situation where we could control temperature. On the redesigned system then, we expected that absorption rate should increase and then go to a constant value. And this is what the data looked like in agreement with our. So the hypothesis, skin senses chemical absorption and changes to slow it, fails. But what we do know is that the absorption rate is constant if we can keep the concentration constant. So after this result, we set about doing a whole bunch of experiments, and we published some papers. And I'm not going to tell you about those today because you don't want to be here till 8 o'clock. But based upon that successful collaboration, I started to think about what other opportunities would exist for a chemical engineer to study chemical absorption into skin. And I thought, well, with the background that a chemical engineer has in chemistry, math, and physics, combined with some expertise in thermodynamics and mass transfer, if I combined those with expertise in some other fields, and by the way, I've worked with people in all these fields, that we could probably answer some pretty interesting questions. And some of these are questions and ones you probably have thought of yourselves. So, can a drug be effectively and safely delivered from a patch? Remember, this was in the early days. Patches hadn't been around so much. They weren't common. Is that generic topical cream you're using as good as the one from the original manufacturer? You just discovered that your drinking water is contaminated, and so you're not going to drink it. But is it OK to shower? What about all those products you use around your house? Cleaners, soaps, paints, the insect repellent and sunscreens you put on your skin, cosmetics, hair dyes, are they safe? You just applied pesticides to your lawn. When can you let your kids play in it safely? Is the skin contact you have with chemicals at your job safe? And I think this one's kind of timely. Is it safe to walk barefoot on a beach that's been contaminated with spilled crude oil, even if the amount that's there is too small to see? The good thing about all these questions is they're very diverse, and so there were a lot of different funding agencies that would be interested in them. So I found a research topic that could be funded by more than one agency, and I jumped on it. So to summarize this part, the second story, you know, the research topic that I've worked on for the last 25 years, I discovered by accident. And even better than this everyone likes my research. When someone says, what kind of research you do, they always seem really interested in. And that's because everyone is, including all of you and me, wrapped up in my research project. All right. Last story, chapter 3. Much more than its name. This is the story of bioengineering and life science at mines. Now, I remember when George Ansell became president, he described that period of falling oil prices and mineral prices and declining student enrollments. And he said you either had to change the world or change the school. The school had to change. And so the school set about making a change. Really, the goal was financial stability. And it set about to achieve this in 3 steps. The first step was to increase student enrollments. The idea was to diversify the degree options to make mines attractive to a larger group of students. The second step was to reduce impact of economic cycles in the energy and minerals industries, the industries we'd worked in for more than 100 years, by broadening the base of support of these supporting industries, and especially the employment opportunities for our students. And the last step was to increase research revenues. Really, the idea here was to separate how many faculty we had from how much student enrollment. That if you increase research revenues, you could hire faculty, even if you didn't necessarily have a large increase in student enrollment. Now, with this new idea of who we were, our marketing materials had to change too. And in 1986, you see this change. We declared ourselves Colorado School of Mines, much more than its name. Don't laugh. This thing has gone in and out of vogue, and it was in just a few years ago again. Now, I always laugh at this particular document because we were still in 1986, this was a really brand new idea, and we still weren't quite used to it yet. We weren't quite sure about who we were. But we got the message sorted out by 1989. By then, the image at least we're portraying is that we're definitely no longer just a minerals engineering school. And we've struggled off and on with the tagline to try and describe ourselves. This year, it was much more than you imagine, and it's actually quite an interesting exercise. I've done it. I was going to include it. It just, again, you didn't want to be here till 8 o'clock. It's quite an interesting exercise to see what taglines we've used to try and describe. We really have a hard time with this. As we expanded our degree offerings, it meant that we hired a more diverse faculty. When we hired a more diverse faculty, we had expertise in a broader range of areas. This had a positive effect on our traditional programs because we brought new ideas to them that they could use. As these new areas developed groups of faculty with similar expertise, we began to form groups. And as those groups grew, eventually, in some cases, you reached enough that they sort of began to have a positive feedback. You might call it they'd reached critical mass, and now the group was large enough it caused another increase, and so on. I sort of diagrammed this here. I hope you like this. It took me a while. OK, so you have faculty that are interested in BELS. BELS is bioengineering life sciences. They teach courses and do research, and students get interested. They ask for more research and more courses, and the faculty oblige them. And that means more students are interested in bioengineering and life sciences, and they ask for more courses. And the faculty now has to grow because you need more faculty to teach all of those. And then they teach more, and students grow, faculty grow. And you can see pretty soon you have enough courses, students, and faculty in the program that you can organize a curriculum around it. And that's exactly what's happened. So if we look at the number of faculty that we can identify as having specialty in bioscience and biotech, since the decision to diversify degree options in 1986, you can see that it's grown dramatically. And in 2009, thank you, Dave Marr, for these data. By 2009, and I didn't add the last year. He didn't send me 2010. 10% of our faculty. And the faculty working in the biomed subspecialty was just under half. In 2001, BELS really got formalized because it appears in the student bulletin. And prior to this, we were teaching courses in bioengineering and life sciences, but where we would put them is in the departments that they sort of fell into logically. So mathematical biology was a math course. Biology was a course in the environmental science and engineering department. But there were a few BELS courses that just didn't fit. So who would know? that Math 498D was anatomy and physiology. And what happened was the person who was teaching this course happened to be a member of the math department. That person, by the way, was Hugh King, who's also an MD. So it isn't illogical as it seems at first. Now, these problems were resolved in 2003 when the Bell's curriculum was established. And bio keeps playing a bigger role. By 2007, we have our first bachelor's degree with a bio in the title, biochemical engineering. And in chemistry, then, you can now get a biochemical track. 2008 was one of those big years because we finally offered biology labs at Mines. Students for a decade now, it's sometimes been required to take, who were taking biology had to take a biology lab. It was required, but they had to take it at Red Rocks Community College because we didn't have one. So now biology labs are taught here. If we look at the research volume that can be attributed to bioengineering and life sciences research, you can see it's been increasing dramatically, reaching 15%, roughly, of the total research volume of the institution in 2009. And you don't have to look any further than our webpage to see that bioengineering and life sciences have become important. If you pick the tab for prospective students, you find this question there: do you want to solve everyday problems that improve lives around a global community by, and then it gives them 6 examples. 2 of them are biology, bioengineering, life science. Develop pharmaceutical medications, design artificial limbs. So what can we say here? Well, we can say that broadening our degree requirements in response to falling prices in oil and minerals caused Mines to transform itself from an institution of mineral engineers to include bioengineers. And in fact, if you read our documents today, bioengineering life sciences are now considered fundamental to the role and mission of Mines. Changing times, changing minds. 3 stories that in different ways describe those 3 actions: making a plan, seeking diversity, enjoying serendipity. I can't miss this opportunity of a public lecture to have a chance to thank a few individuals who've played a significant role in my career. First of all, I've enjoyed great support over many years from my department heads: Art Kidney, Bob Baldwin, Jim Ely. Those of you who know me know how important my running partners are. They've been my counselors, my mentors. They've listened to me a lot and been good sounding boards, preventing me from doing really stupid things sometimes. Dundee. I've had many over the years, but these were the ones that I probably put the most miles in. My current running partner, Reuben Collins, deserves special mention. First of all, he had to hear about this lecture for 9 months. And then he consented to be the man of honor in my wedding. I need to thank my husband, Rob Raker. I should point out this is not the same husband that went to work on the Colony Project. For his love and support, but most of all for his patience in putting up with me saying I can't do things with him because I have this big deadline. And thankfully, this one's just about over. I haven't talked very much about my research, but it wouldn't have been possible to succeed in that area as I have if it wasn't for funding agencies and my many collaborators, students, and postdoctoral fellows. I want to thank various individuals for assistance in providing information with this presentation, especially Ethan at the bottom there. He went through 36 years of faculty bulletin, or student bulletins to count the number of faculty. Heroic effort. And last of all, I want to thank you. Thank you for coming. And I'll leave you with this final message and open the floor to questions if there are any. Thank you.